All right, now that you've had an intro into waves themselves and kind of how they work and what their parts are, we're going to take a look at measuring a wave. And we're specifically going to be looking at things like wavelength and frequency and prop speed today. So this is measuring a wave part one. So first of all, just a quick recap of what we talked about in the last video. The wave properties here. This is a longitudinal wave. As you can see, the molecules are moving side to side here, and they're compressing and then they're separating. So this is a longitudinal wave. Remember that compressions are areas of high pressure where they are pressed together, whereas a rarefaction is an area where the molecules are more spread apart, the particles are more spread apart, and then we have the wavefront or the movement of the wave in one direction. And also remember quickly that the longitudinal wave is difficult to study in the longitudinal format, so for simplicity's sake, we look at it in the transverse format. So we have slightly different wording. We have crests for the peak of our wave. You can think of like the crest of a wave if you're a surfer. It's the very tip top of a wave. And then we have the trough being the bottom of the wave. You can think of like a horse trough where all the water is held inside so the horses can drink. We also have a couple other words here that I wanted to point out. You don't have to worry about elevation too much, but we do have wavelength, this red arrow here. This is a new word that you'll have to worry about. Wavelength and amplitude here is also going to be important, not for this time around, but it will be important later. So now that we've seen the transverse view, let's take a look deeper into these different pieces parts. So let's look at wavelength first. Now wavelength, when we write it out in an equation, we have other equations that use the letter W, so we can't use the letter W, otherwise physicists get confused. So instead we started borrowing from the Greek alphabet, and the word that we picked up was lambda. This letter is called lambda. But it basically, you can think of it as like a high heel. It looks like a high heel. Um, and a wavelength is the distance between similar parts of a wave. Usually we refer to them as crest to crest or trough to trough, but it can be any part of the wave as long as they're similar. And for our purposes, we usually measure it in millimeters, or we'll have to convert it into millimeters usually if we're doing an equation. So if we can see here, I have two different waves with two very different wavelengths. So you can think of wavelength, the length of a wave, just like if you're measuring the square footage in your house and you want to know how long one wall is. It's the same kind of idea, only this time we're measuring the wavelength. So we have the wavelength here from crest to crest, and we have a pretty large wavelength. There's a large distance between the two crests. The wave down here, wave letter B, this one has a much smaller wavelength. The waves are closer together, so the wavelength is actually much smaller. Kind of like having a 10-foot long wall versus a 5-foot long wall. So that is our wavelength. Next piece here is the propagation speed, or prop speed, you might hear it referred to as. Prop speed is indicated by the letter C because, again, P is another word that we have, or another letter that we use in other physics formulas, so we use the letter C, and C also refers to prop speed of pretty much everything. We can also have prop speed of light, or the speed of light in Einstein's famous equation E equals mc squared. The C there is speed of light. So we use the letter C for propagation speed. And prop speed, in brief terms, just means how quickly sound can travel through a medium. We're going to use sound specifically, but how quickly that sound can travel through a medium. And it depends really on the density and how thick the medium is. The different properties of, if the particles are closer together, they're easier to bunch up, so it will pass through it a little bit nicer. For example, air molecules are very spread apart, so creating things like sound waves that travel through air is actually pretty difficult. So the speed isn't very high because it's going to take more effort to press those air molecules together. Whereas in something like water, in water or liquids, the molecules are actually closer together, so it's easier to push them up and make those compressions and rarefactions. So it's going to move, the sound is going to move faster through water than it is through air, just because of the molecules being closer, the particles being closer together. When we are talking about prop speed, we will measure this one in millimeters per microsecond. You can think of this as like when you're driving a car and you're like, I'm driving 50 miles per hour. You would write it the same way. It would just be miles over hour. But in this case, oops, in this case, it's going to be millimeters per microsecond. In soft tissue, we are going to use the constant value of 1.54 millimeters per microsecond. That's going to be our prop speed of soft tissue. It varies a little bit because every soft tissue is a little bit different. Like if you think about liver cells versus a pancreas cells, they are slightly different in their composition, but in general, they average out to about 1.54 millimeters per microsecond. So that's the number we're going to use. And this wave here is just to remind you of what the particles have to do in order to create that wave. This is a transverse wave that I'm using in this example, but you can see if the molecules are closer together, it's easier to move them. If they are further apart, it's more difficult to create that wave. That's why prop speeds are really high. It goes really fast in substances that the molecules are closer together, like liquids, like water. Whereas air molecules are really far apart, so it's harder to push them together. It's harder to make that motion happen. So prop speed in air is actually much slower. Okay, so that's prop speed. Now let's take a look at frequency. Frequency is how many waves pass through a point in 1 second. So if we take a look here, I have two different waves. The wave on the top has a really big wavelength. There's a lot of distance between the waves. Now, because there's a lot of distance between the waves, not all of them can reach this point very quickly. So if we take a look here as the wave is propagating, as the wave is moving along, let's see if it passes this point, how many we can get. So you have 1, 2, 3, 4, so like that. So this wavelength, this frequency is very low. Whereas this wavelength down here, this wavelength is much smaller for this wave. But since the wavelengths are smaller, you can fit more waves in the same space as the one above. So if we take a look at the waves passing this point here, we have 1, 2, 3, 4. It's much quicker. So the frequency is higher in this bottom wave, and it's lower in this wave. However, as you probably noticed while we were talking about this, the wavelength is actually inverted. The longer the wavelength, the smaller the frequency. Let me say that again. The larger the wavelength, the smaller the frequency. And that's because just like if you're trying to put more boxes into your car, let's say you're moving, if you have more boxes in your car, the bigger the boxes are, the fewer boxes you can fit in your car. In the same idea, the bigger the waves are, the bigger the distance between the waves, the bigger the distance between the waves, the fewer you can fit in 1 second. The smaller the distance is between the waves, you can fit a lot more within that 1 second. So that is frequency. Those are the three properties I want to talk to you about today: the wavelength, the prop speed, and the frequency. Now let's take a look at some equations. Let's use some of these in our equations here. So I'm going to adjust my screen. Okay, so I've adjusted the screen so you can see both the equations, the PowerPoint, and also the whiteboard where I'm going to be doing some drawing. So before we get into all of this, I just wanted to let you know what the equation is for using these three objects here: the wavelength, the frequency, and the prop speed. I'm going to give you this one. So wavelength, which is that lambda sign, remember, equals propagation speed, which we indicate with c, divided by frequency. All right, now hold on to that, and we're going to get into the metric system really quickly, because the metric system is what we're going to be using, we're going to have to use when we're doing any equations. Fortunately, the metric system is actually a lot easier to use than the version that we Americans use here. So the metric system is based on what we call a base 10. So that just means you keep moving your decimal place in order to get to the next unit. So I have this broken down here. I have the prefixes on the far left, I have their symbols, and then I have their multipliers. So let's first just look at the prefixes themselves. So we have mega. Mega is our first prefix. And this could be, you would put the prefix mega in front of any measurement that you wanted. So you could have megahertz, you could have megameters, you could have megaliters. It could be anything, but the prefix mega is going to be our top prefix here. There are more that go above mega, but we're not going to worry about them. We're going to focus on mega only. Now the symbol for mega is a capital M, and that's going to be important in a second. The next one we have down is kilo. So you might have kilometers, kilometers. You might have kiloliters. You could have kilo of anything, but that's the prefix here is kilo, and the symbol for that is K. Then we have hecto and deca. We usually don't use these two, so I'm not going to emphasize those too much. Then we have our base unit. This is our number 1. This is basically prefixless. It does not have a prefix. Then we have deci. Again, we don't use very often, but you could see like decimeter, but we don't use that very often. I'm not going to emphasize that too much. And then we have centi. Centi we do use. If you think of century, century is 100. You want to think of that when you're thinking of centi as a prefix. And the prefix and the symbol for centi is going to be the lowercase c. And then we have milli, and milli is a lowercase m. Remember that mega is a capital M, milli is a lowercase m. That's going to be important because when you're reading the problems, if you see a capital M, that's going to be way different from seeing a lowercase m. And then our prefix on the bottom here is micro. Micro, again, we had to borrow from the Greek alphabet, and so it looks kind of like a U, but with a tail in the front. So that's our micro. Okay, now what do these mean? So I told you that these are prefixes. If you add them to your measurements, they mean something. Mega means that you have 10 to the 6 of that thing, or in other words, a million of those things. So if I say I have a megameter, that means I have a million meters. Kilo is 10 to the 3rd. So if I say I have a kilometer, a kilometer, that means I have 1,000 meters. And then my base unit here is just 1. That means if I have a meter, that meter doesn't have a prefix in front of it. So a meter is just a meter. If I have a centimeter, that means I have 10 to the negative 2, or 1/100th of a meter. So don't confuse centi with hecto. Hecto means you have 100 of it. Centi means you have 1/100th of it. In other words, 0.01. Milli down here is our inverse of kilo, basically the opposite of kilo here. Millimeter means you have 0.001 meters, or 1/1000th of a meter. And then micro down at the bottom is 10 to the negative 6, which is, here you can see here, 0.000001. So those are prefixes, and that's what they mean. So what good is it for us to know this? Actually, it's a lot easier for us to know these and convert these, because you might be given an equation, let's say wavelength. Wavelengths we usually measure in millimeters. But let's say that your equation or the word problem gives it to you in centimeters. Well, you're going to use this metric system in order to convert to that new value without losing any of those meters. That's the crucial piece with math, is you never want to lose numbers. So the metric system is based on a base 10 system, which just means that you have to move the decimal place. And then when you add that prefix on there, that means you have the same number, but now it's in a different value format. So for example, if I'm converting 5 meters to kilometers, meters does not have a prefix in front of it. It is the base unit. So we would start at our base unit. And then I'm trying to convert it to kilometers. I know kilometers is to the negative 3. or I'm sorry, to the 3. Kilometers is to the third. So I know that there's deca, hecto, and then kilo. There's 3 spots before I get to kilo. So I know that all I have to do is move my decimal place 1, 2, 3 places to the left. So in 5 and whole numbers, the decimal place is always at the very end. So I grab that decimal place and move it 1, 2, 3 spaces to the left. Let me write it out here on our whiteboard. Okay, so I'm just going to write down quickly the prefixes. So we have mega, we have kilo, we have hecto, deca. We have our base unit. I'm just going to indicate it with a U. And then we have deci, centi, milli, and micro. Okay, so we have all these prefixes here. Now let's say I have this number 50 micrometers, or micrometers as we might say. Since it's a whole number, my decimal place is right here. Does this have a prefix in front of it? Yes, it has micro in front of it. So I know that when my starting range, when I'm starting out to convert this, I know I have to start here on that same prefix. Now let's say I want to convert it to kilometers. How am I going to do that? Well, since it's base 10, all I have to do is count how many prefixes separate me from where I start to where I'm ending. So I want to end on the K, and I'm starting on the micro. So if I go 1, 2, 3, 4, 5, 6, 7. I'm moving 7 places to the left. So in the same way, I'm going to take that 50. Let me erase the question mark there. There we go. I'm going to take 50, grab that decimal place, and move it 1, 2, 3, 4, 5, 6, 7. And I'm going to plop that decimal place there. And all of these empty bowls that I made, I'm going to fill in with zeros. Anytime you have an empty bowl, you're going to fill it in with zeros. And there we have it. So my answer, 50 micrometers, is equal to, it's the same value as 0.000050 kilometers. All right, let's go the other direction just so you guys can see it. So again, I have my prefixes. Got mega, kilo, hecto, deca, my base unit, deci, centi, milli, micro. Let's say I want to go the other direction. I have 500 kilometers. And let's say I want to go to centimeters. So first we look at where we're starting. So we have kilometers. What's the prefix here? It's the kilo, the K. So I'm going to start on the K. Whoops. I'm going to start on the K. Now where do I want to end up? I want to end up on centi. I want to end up on centimeters. So I know I want to end on the C. So what do? I just count how many letters separate me from where I'm starting to where I'm going. So I go 1, 2, 3, 4, 5. I went 5 places, but I went to the right this time. That's going to be crucial here. Now, in my number 500, since again it's a whole number, we're going to have a decimal place at the very end, after the last number. So let's see what that turns out to be. We take 500, and we're going to move 5 places to the right. So I'm actually going to write it out here because otherwise it'll get messy. So 500, I have that at decimal place, so let's grab it and move it 5 places to the right. 1, 2, 3, 4, 5. I put my decimal place here, fill in the space with zeros. So 500 kilometers is the same as having 5, let's see, 1, 2, 3, 1, 2, 3, 50 million centimeters. So that's how you would convert within the metric system. All right. Now that we know that, now that we have that down, make sure to go back and review this if necessary. Now that we have that down, let's take a look at some example problems that will use those 3 properties of waves that we rehearsed earlier. Remember, wavelength is the distance between 2 similar parts of a wave. Then we have the prop speed, or how fast the wave can travel through a medium, divided by the frequency, which is how many wavelengths can pass a certain point within a set time. So our equation for that is going to be wavelength equals prop speed divided by frequency. So let's take a look at example problem number 1. It says an ultrasound wave has a wavelength of 0.59 millimeters. What is the frequency of this wave through soft tissue? Okay, so now we have some pieces here. So let's indicate our necessary parts. Do we need to know it's an ultrasound wave? Not really. That's kind of unnecessary. Do we need to know the wavelength? Yes, definitely. That's part of our equation. So we have the wavelength is equals 0.59 millimeters. And it's asking me what is the frequency. So frequency is what we're solving for. Next piece here, through soft tissue. Okay, so it tells us specifically that we're traveling through soft tissue. The value that we talked about earlier, that is our default for soft tissue, is prop speed equals 1.54 millimeters per microsecond. Now it's going to be crucial that we know this information here. So we have 0.59 millimeters per, and then we have 1.5 millimeters per microsecond. First, check to make sure that your units are similar, because they're going to have to cancel out. I'll explain that in a minute. But we have millimeters here, and we have millimeters here. So we're golden. We're good. We're good to proceed with this equation here. So we're going to plug it in here. It's just plug and chug, basically. So we've got a 0.59 equals 1.54 divided by our frequency. Okay, well now we're kind of stuck because the frequency is on the bottom of our denominator. Don't worry, only thing you have to do to get something from where it is to where you want it to be is to undo whatever it's doing. So right now, my frequency is being divided on this side. So all I have to do is the opposite of division, which is multiplication. So I'm going to multiply by f. But whatever I do to one side of this equal sign, I have to do to the other side. Think of it as like a teeter-totter. You have to keep both sides balanced. So whatever you do to one side, you have to do to the other. So I'm multiplying both sides by frequency. So since we've got one dividing and one multiplying, they cancel out. But on this side, the f stays. So we have f times 0.59 equals 1.54. All right, halfway there. Now the f is still doing something. It's still not by itself. So we now have to undo whatever it's doing on the other side. Well, right now, it's multiplying itself by 0.59. So we want to undo that. We want to get f by itself. So what we're going to do is we're going to divide both sides by 0.59. Since 0.59 is the same as 0.59, they're going to cancel out. So we're just left with f on this side. And now, using a handy-dandy calculator, or if you are a human calculator, then you can probably do this on your own, but we have 1.54 divided by 0.59. and that gives us a value of about 2.61. All right, great, we calculated frequency, but we're not quite done yet. Remember that frequency also has units. So our units for this guy is going to be megahertz. So I'm going to write that out. Remember, it's going to be a capital M because it's mega and not milli. So there is our final answer here to our sample problem number 1. So the frequency of this particular wave is going to be 2.61 megahertz. All right, great. That was our first problem. Let's take a look at another one just to see, make sure that we're all on the right track here. So example problem number 2. A certain sound has a wavelength of 0.032 meters. Calculate the frequency of this wave through soft tissue. Okay, now this one's a little bit more tricky because as you can see, we have the wavelength, we have soft tissue, we have frequency. Okay, great. We're still using that formula that we mentioned earlier. Wavelength equals prop speed over frequency. However, in this sense, we have 0.032 meters. And if we write that out, wavelength equals 0.032 meters. Prop speed is 1.454, millimeters per microsecond. And frequency is our unknown. Well, now our units don't match up. We have meters here and we have millimeters here. So if we were to just plug in this wavelength, it would not give us the right answer. So what do? Well, remember we talked about the metric system earlier and converting within the metric system. So we have to convert meters to millimeters. Now, if we look at meters, does it have a prefix? No, it doesn't have a prefix. So that actually makes our job a little bit easier. So we know that the prefixes, again, mega, kilo, hecto, deca, base units, deci, centi, milli, micro. Meter is going to be our base unit. It's the one indicated by a U. And we want to convert it into millimeters. So that way it can be the same as our prop speed. So I go 1, 2, 3, 3 spaces to the right with my decimal place. So I have 0.032 meters. So if I move it 3 places to the right, 1, 2, 3, I have 32 millimeters. There we go. Now do the units line up? Yes. Now we can plug and check. Now we can put our numbers into this equation and make it work. So we've got, let me write this out again. So remember our equation. And wavelength was 32 millimeters. Prop speed, it's soft tissue, so it's 1.54 millimeters per microsecond. Oh, my tail got a little long there. And then our frequency is what we're trying to solve. So again, we're going to put 32 on this side equals 1.54 over F. Multiply F by both sides. So we have F times 32 equals 1.54. Divide both sides by 32, so we have F by herself. And then we have 1.54 divided by 32 is 0.048. And what were our units again? Megahertz. Megahertz. Capital M. And there you have it. We just figured this one out. Awesome. If you guys are keeping up with me, Then I'll show you two more problems that I'd like you to solve on your own. I'll help you figure out some of the trickier parts, but I want you to solve them on your own. And remember our equation. Wavelength equals prop speed over frequency. So example problem 3. A transducer produces waves at a frequency of 590 kilohertz. What is the wavelength of the waves through soft tissue? So this one is slightly different. Before we were solving for frequency. Now we have a frequency and we're trying to calculate the wavelength. We know it's through soft tissue, so we're still using 1.54. Think about what you need to do to frequency first before you plug it into the equation. So pause the video here, take some time to solve this equation here. All right, let's move on to example problem number 4. A transducer emits energy with a wavelength of 12.9 centimeters. What is the frequency if the prop speed is 1.30 millimeters per microsecond? So with this one, there are two things that you're going to have to keep an eye on. Wavelength is now in centimeters. What do you have to do to wavelength before you plug it into our equation? Also, the prop speed has changed, so don't get confused. Make sure to use the correct prop speed. Okay, hopefully you did well with those sample problems. Now, if you need more practice, be sure to leave a comment and I will come up with some more practice problems for you to do. But those are the wave properties. Feel free to rewind this video and re-watch the parts that you are still confused on and go ahead and solve those problems.